Hello everyone, and thank you for joining us today. My name is Reidun Dallen, and I'm the market manager at Aanderaa and have been working with the MOTUS team since its launch approximately 1 year ago. I will also be happy to host today's event. During this webinar, you will be able to hear the presenters, see the slides, and ask questions via the chat box on the right side of your screen. We will also address these during the Q&A session at the end of this webinar. Unfortunately, we cannot see you or hear you today, but our system tells us that you are online. Please note that the webinar will be recorded and made available after the webinar. So I think that concludes the practical information, and we can move on to today's topic, which is MOTUS Wave Buoys, 1 year of experience. And I will let the presenters introduce themselves. Emily?
Okay, thank you, Reidun. My name is Emily D'Angeville, and I work at Aanderaa as a product manager for the wave and current solutions. I have been working with Aanderaa for more than 10 years, and I had the chance to be part of the MOTUS project, which has been a very exciting project for us at Aanderaa and Xylem. Now we are reached with more than a year of data, and we have the pleasure to present the experience we gained since the MOTUS sensor release.
Thank you, Emily. Inger?
Yes, my name is Inger Graves. I am the Ocean and Coastal Business Development Team Leader here in Europe. The business development team in Xylem Analytics works across the product lines and finds solutions combining several product lines. And the MOTUS Buoys is really a true cross-brand solution with products from many of our main brands in the Ocean and Coastal segment. So we've been working on it together with the other brands of Salmon to come to the MOTUS solution we have today. So if we go on, Emily and I will go through this presentation together. The agenda is as follows. First, we'll do an introduction and a reminder of what the MOTUS concept, the MOTUS Buoys, are about.
Then we will continue by presenting some projects where the MOTUS buoy has been used for monitoring the environmental conditions.
We'll then turn to some fascinating data validations coming out of the demo buoys that we have running for more than 2 years now and off the Norwegian coast.
And then we will finalize this webinar by presenting some interesting phenomena that have been observed in the collected data.
Okay, so before we go into the details, we'd like to remind you that there was a webinar last year, a little bit earlier in the year, where we did go into the details of MOTUS. And this webinar can be accessed still in a recorded version. So if you would like to go into the details of the sensor and buoy interaction, then that is a recording for you. So what we'll do now is just to sort of quickly summarize the main features of MOTUS.
Okay, so when we started the development of the MOTUS sensor, we had in mind to solve the challenges that are related to wave measurements from buoys. So the goal was to develop a sensor able to be mounted on any type of buoy, including non-ideal buoys. And by that, we mean buoys that are not specifically designed to follow the water surface displacement. So as power is often a challenge for buoy system, we spend a dedicating amount of our R&D efforts to optimize the performances of the sensor and to reduce the power consumption. So today, the MOTUS sensor is the wave sensor with the lowest power consumption available on the market.
Also, features for compensation for buoy response were incorporated in the sensor, and this makes it possible to use these non-ideal buoys that Emily was describing to measure the waves. So in this picture in the middle here, basically a large buoy tends to suppress maybe very small waves, and what we built in was ways to compensate that effect out to really become a very accurate solution on these buoys.
And also, it is not always possible to position the sensor in the buoy center of gravity. So we have implemented a function that allows to compensate when the sensor is positioned off the center. Like, for example, we've done a test and we positioned the sensor 50 centimeters from the center of gravity, and we could notice some errors up to 15%.
Yes, and in addition, of course, part of the reasons we wanted to use such a bigger buoy was we wanted to be able to use a standard buoy that was in deployment many places in the world, that was proven, and there were proven buoys. We have several. We have two, obviously. And we wanted to be able to build flexible configurations so that you could use it for measuring waves and currents, but also measure above water, meteorological parameters, and you can vary your payload in terms of what type of data communication that you used, and so on. So our solution is really also the flexibility of positioning the sensors and the different types of equipment on these standard buoys.
Right. One of the issues also while using buoys is that you may have some magnetical interference from the buoy itself or from the mooring line. With the MOTUS sensor, it's possible to directly connect an external compass that could be located further away from the magnetical interference.
And also, of course, we built this on the products that came out of Xylem Analytics, and we are fortunate to be able to cover the major functionalities that we wanted with internal products. So we had, as you can see here, both current measurement solutions, water quality solutions, and data loggers internal to the company that we used in the total solution for the MOTUS buoys. So let's look at some of the challenges. And first, let's start with measuring currents from larger navigation buoys. What sort of challenges do you see, and did you see there, Emily?
Okay. So first, as the same as for the wave sensor, we have a compass in the Doppler current profiler sensor, and the compass is sensitive to magnetism. So here, if you have a magnetical disturbance from the buoy to the sensor, you also have a possibility to interface an external compass to the sensor for compensating of this issue. Then another problem is the position of the sensor. When you position the profiler under the buoy, and because you have some movement with the waves, one of the beam will meet the mooring line maybe, or it will be disturbed by the moorings. So here we have implemented what we call auto beam combination. So if one of the beam meets the mooring line, we can remove automatically the faulty cells. And also we compensate for the movement, because when you have the movement from the buoy, the beams will be moving back and forth in the water column. So we want to position the cell at the right level, and we do some tilt compensation for everything.
Yes, and as you see in this picture here, this is the the DCPS that we refer to. For those of you who don't know our four-letter acronyms by heart, this is Doppler current profiler sensor, and these are the ones that we are using to profile currents from the buoy.
Okay.
Yeah.
And then we also have solutions for monitoring the water quality. So Inger, can you tell us more about that?
Yes, we wanted to also be able to offer this as a standard package on the buoy with MOTUS sensors on there. And we have several solutions within Xylem Analytics. If fouling is an issue, which it typically is when you're in the upper layers of the water, we have sensors such as the XO3 that really provides an anti-fouling feature that prolongs really the maintenance intervals of measuring water quality from a buoy. We also have, if you need just single sensor or fewer sensors, you have single sensors here from the Aanderaa side that can be mounted on the buoy. These will require some different types of anti-fouling to be able to prolong its deployment. All these sensors typically are positioned in the moon pool or a hole in the buoy, like you see on the red buoy below here. And the standard functionality that we put together includes that we have racks that make it very easy to uncover these sensors for regular maintenance to keep the accuracy up and running. Okay, and then we have waves, of course. And Emily, let's look at some of the challenges with wave measurements.
Okay, so if we look at the challenges with wave measurements, we actually have three main methods to measure waves. There are dedicated wave buoys, but they only measure the wave parameter, and they also may have some limitation in the real-time options. and they also offer very little flexibility in terms of parameters to be measured. One of the challenges as well is the robustness. They are quite sensitive to robbery and accidents.
And then I think you also have seen also in the larger waves that we will see in the data that when we correlate with these small buoys, they're also losing their signals. You won't
exactly. They can be also submerged under the water surface, which could be a problem as well.
And of course, the standard bottom mount has its limitations as well, or its challenges. Cabling and real-time solutions are expensive. Sometimes it's hard to find a good place to get the cabling, to get the cabling into shore. And also, of course, cables are sort of the weak point of installations typically, and the long cables are, of course, specifically prone to problems if not protected correctly. So the accessibility and maintenance costs will typically be higher here, where you have to uncover or recover these systems, maybe in many cases using a diver. These solutions do have their limitations in the way of access, I would say. As for large buoys, what we set out to do something about.
And for the larger buoy, one of the advantages is that they're larger, so they can provide a better autonomy and offer longer deployments. So they can also be used for several purposes, like navigation, signalization, and also you can use them for monitoring the complete environmental conditions. But so far with these bigger buoys, it has been a challenge to measure the waves accurately, which is what the MOTUS sensor has been challenged to solve.
So let's go and look at some of the user stories that we've had from the last couple of years. Oh, from last year's, typically. Sorry. So why do we measure waves? I think that our users all have a different perspective and a different reason for measuring the waves. And we've picked some of the stories that offer a little bit of a difference in the reason for measuring wave height and wave direction.
So here is an example of a system that we have delivered with our partner Salmon in Spain. So this is a project for the Port Authority of Cartagena, and there we deliver a tidal buoy that join a buoy network that is operated by the Spanish Port authorities. So these buoys in this network, they are equipped with a meteorological, currents, and wave sensors, and they are used to provide real-time data to support navigation and also to improve port operations. So here is a satellite image of the buoy location. The buoy is positioned 7 kilometers from the coast, and it will help the vessel traffic to access the channel to the port of Cartagena. And they provide in quasi real time the information about the state of the sea, including directional wave, currents, and wind. And this is an example of the data that will be transmitted. So the buoy is supplied with a GeoView, which is an Aanderaa display here on the left. So on the upper part, you can see these are some example of wave data, and then on the lower part here is the current information you can see at different level. And then those data are also sent further to a web page that is used by the Spanish port authorities, and also is made available to the general public. Yeah, so that is one of an example. And you, Inga, do you have any exciting project you can tell us about?
Wow. So I wanted to share the project we're building, the new breakwater. This is a different type of customer, a dredging customer, who was building a breakwater in a very exposed area. So typically these are constructed with stones and gravel and different types of materials to protect the shores from waves, basically, to either create a shelter or maybe to make sure that there is you have control of erosion on the shore. So our client was building such a breakwater in an area that was away from the major port where they could have their equipment. And as you can imagine, building breakwaters, putting this together, you have to rely on fairly calm conditions. So they wanted to be able to figure out if they were able to do construction in a certain day. So they were able to monitor this site that was further away from the port and to check and see if the swells and the waves were beyond what they could sustain with their equipment before starting to mobilize and moving their transporting their equipment 2 to 3 hours to the site. So the buoy solution was constructed to be able to give them this real-time data over different channels also, because they needed to be able to, they weren't relying on the mobile network to always be available, and they wanted to be able to also send data on alternate channel Iridium. But what they also wanted to do was to be able to use this buoy once the project was done for other projects, and flexibly and use the flexibility to try to, or to use it in one way with certain package of sensors in one project, and then in the next project use maybe different communication solutions and different sensors on the same buoy. So they use both the flexibility of the MOTUS sensor, of the MOTUS buoy, as well as the ability to host this variety of sensors in this project. Okay, and then we wanted to look at some aquaculture projects.
So here is one of the projects we've been involved with for salmon farming in Tasmania, because the production has increased dramatically those latest years. They have an increased need for monitoring the environmental conditions. So the seastate conditions are very important for them, as well as the quality of the water where they produce the fish. And they also need to understand better the weather and ocean influences on the farming. So here we supplied a buoy with the MOTUS sensor. They also measure the currents, and they have an EXO for the water quality measurement. So data, they are transmitted into real time, and they are made available for operational decisions, so they can plan according to the weather and ocean conditions. And they are also used to ensure the safety needs. So here on this drawing, on this graph, you can see some example of the data they will get in real time. So that was an example as well.
Okay, so these were 3 examples of uses of the MOTUS buoys with different reasons for selecting this solution. Now we want to turn to look at some of the data and a comparison test and the data that we've collected during the period before the release and after the release, to really validate the solution in different conditions and different variables affecting it. So Emily, why don't you tell us a little bit about who you've been collaborating with in this?
Yeah, so when we started the development of the MOTUS sensor, we've been approached by some research institute, and then we started a collaboration. So it has been part of the MAROFF project. And we have been working with a Freeman Research Institute here in Bergen, and each of them have been responsible for one part of the project. So CMR, which is the Christian Mikkelsen Research, they have been responsible for the validation of the technology. So they have been using some simulation, and also, as you see on the picture here, some tests to validate the IMU that we use in the sensor. And they have also been responsible for uncertainty analysis. Then the Norwegian Meteorological Institute, they have also been part of the project, and they have been in charge of the data validation from the sensor, and also comparison with some models they use for forecasting. So mainly the SWAN model. And also the Uni Research Polytech, who have been responsible for the data validation and also field testing.
And then let's look at some of the buoys that were used for the prolonged experiments.
So for the data validation and the test field, so there have been 3 buoys that have been deployed off the north coast of Norway. And here we decided to use two buoys from the Xylem Analytics, the Thailand buoy and the EMM2.0. So we had in mind to qualify those buoys for the MOTUS sensor. So the site was chosen in order to have the most stable field that the free buoys will see the same field. So that's why we choose this site. So there it's about 5 nautical miles from the coast. So we have been deployed a Datawel Waverider, which is used as a reference. And then you have the 1 Thailand buoy that measures the wave, the surface current, and also as a weather station for meteorological data. And we have 1 EMM2.0 buoy that has 2 MOTUS sensors, so one located in the center of gravity and one which is on the outer part of the buoy to test this functionality out of center compensation. And we also have a current measurements using a single point current sensor and a current profiler.
And if we go to the next slide here, yeah, you'll see the YSI EMM2.0 buoy. So as Emily mentioned, there's 2 buoys that were we did the characterization on from Xylem Analytics. They sort of have a slightly different area of use. The EMM2.0 that's here, it's not a navigation buoy, but it does have very good sort of features for data management and protecting of gear. It has an internal container. So on this buoy, we had the smart guard as the controlling heart of the system, which is was also the same for the other Thailand buoy, part of this example. And as you see, 2 MOTUS sensors to check for the, I guess it was the off center compensation, right? Yeah. And then also two different current sensors. One was the profiler, profiling downwards, and also to capture the currents closer to the surface, we used a single point current meter. So those 2 together really covers the range as far as close as you can get to the surface in terms of current, and all the way down to the total range of the profiler, 600 kilohertz profiler. In addition, what you see here is communication solutions, the GPS, the MET, the sort of station up there, and also the what we call the buoy orientation, which is the more advanced version of a compass, along with the solar power solution. So this is all the equipment and that is on this buoy, and that's contained on the buoy that was used for the testing.
Exactly. So then we have a transmission of the data in real time from the free buoys, and they are made available through a web-based database that make it easy to extract the data. So the recording interval is by default 30 minutes, but it's possible to reconfigure it remotely. So through this web-based, it's possible to download historical data for further analysis.
Yeah. Thanks. And then also just to now we're sort of interested in finding out how did you proceed to then validate the data, and how did you go about doing your validation? So because now we want to compare the data mainly to the Datawel to validate our MOTUS data. So we've been using a tool that is called CDIP, Wave Evaluation Tool, and it's a tool that has been developed by Scripps in San Diego, and it's a tool that is widely used by the wave community. So basically, this tool you can do some wave spectral data analysis, and you use 2 data sets, one from the Waverider and one from the MOTUS, and then you do a comparison based on the first 5 Fourier spectral coefficients. And so we want to then look and see what the comparisons showed.
Yes, so if we look at the data that we get from this tool, here you can see you have a comparison of the wave height, the peak period, and the direction, the mean direction. So here we can see that we have excellent agreement between the Waverider and the MOTUS Wave Buoy. And here is another representation where we look at the energy repartition according to the frequency domain. So here you have the frequency and the energy, and we look at some data from a data set from December to February. So when it's blue, it means that you have a very little difference between the 2 data sets. And when it's getting more like this red color here, it's you have higher differences in the data. But basically, the result from this comparison confirms that we have excellent data from the MOTUS buoy. And as I mentioned here, we have a minor deviation in the low energy frequency end of the wave frequency band.
Okay, so you also looked at some of the, you were testing in a lot of different conditions, and I know, one of the tests was, of course, to measure currents and waves and find out the correlation, but you also got some pretty good weather out there, and you got some good data in a variety of conditions. Why don't you tell a little bit about this that we're looking at here, the hard condition with high currents, and how did the wave how did the wave measurements go when you had high currents?
So yeah, that's a good question, and that's here the buoys have been out for more than a year, and they have been experiencing different type of weather and oceanographic conditions. So in this example here, we have an event with a very high current, like 160 centimeters per second, which is quite high. And then if we look at the upper part of the drawing, where we look at the wave height from the wave sensor, from the MOTUS, and from the Waverider, and then we see that we have an excellent correlation. When we come to this event with very high current, here we lose transmission from the Datawel, because as we mentioned earlier, that's one of the problems with these smaller buoys, is that they get underwater when there is a lot of current. Again, here the buoys were deployed at 200 meter depth, so that could be also one part of the explanation.
And I think also that this also gave us a lot of information about what it takes to be out for this long and to withstand these types of conditions in terms of how you mount equipment on the buoy. So this was, of course, very valuable. And also, if we go to the next slide, I think one of the things we were worried about was, how does it work when there's low currents? How does it work when there are calmer conditions? And what can you say about that when there's low currents and high waves, for instance?
Yeah, well, if you use a current profiler especially, and you have a very high wave, then you could expect, because of this movement of the buoy, you could expect some error in your current measurements. So here we have been lucky to have some very high wave currents with a very little current. So if you look on the upper graph here on this slide, we look at the data from the two surface current from the two different buoys, and we look at the first cell from the profiler. And here at the end of the period, we can see that we have very high wave, over 6 meters, significant wave height. And then here we can see that we have current like less than 40 centimeters per second. So that we can see that the free current sensors, they are quite in agreement, even if we have a lot of movement in the buoy.
Yeah.
So those data show and confirm the ability of the MOTUS Wave Buoys to measure accurately waves and currents in varied conditions.
Okay, so now let's turn to a sort of some understanding or some surprising data. I guess looking at this graph here, I would be like thinking that there's something wrong with the data when I look at the current graph that you're showing here. So you explained, you found some really surprising data, and how did you go about, and what did you find out about this data?
So when because we collected a large amount of data, and then when we look at the data, here you can see it's a representation of the currents from the surface down to 12 meters. So you can see that you have some variation, and then just here on the 4th of March, you have very high current, like 160 centimeters per second, and then it goes down all the water column to almost zero. So it's quite a big change in the current conditions. Here, if you look at the direction from the currents, it's also a big change from the direction. So then, yeah, what could be the explanation for that? So then we start talking to the Meteorological Institute, and they explained us that here in this location, in this channel, Skagerrak, there is some eddy forming here, and they move along the coast, moving further north. So here, if you look at the modelization here of the current, you can see that the eddy are forming. So here, if we look at the water level station from here, we can see that 2 weeks before the data we observed, we have an increase in the water level, which is the signature of an eddy forming. So the eddy is forming and then moving further along the coast. And this is what we observe with this data here.
Yeah. So I guess if you were out there sailing along in your little vessel, this could have quite a dramatic effect.
Yeah, it could be quite surprising to
have 90 degrees off. You have a current.
It's a big change in current.
Good. Okay, so let's look at some of the data that's collected outside of the MAROFF project, where the team has evaluated various conditions and sites. Why don't you tell us a little bit more about what sort of, some other interesting data that you've collected to make sure that you covered all the bases in terms of where the solution performed?
So one of the question also is how well do we measure wind waves? So for that, I mean, measuring wind waves it can be challenging when you are using a bigger buoy like the one we do. It's
these are smaller waves that are typically.
The buoy is 1.75 meters in diameter, so it could be a big to measure smaller waves. So for that, we perform a test in the Fjord, and then we use here a Datawel buoy and the Thailand buoy equipped with the MOTUS, and they are separated by 400 meters. So if we look at the data that was collected during this period, we can see that we have a quite good relationship. There is a little bit difference, but this is related to the distance from the two buoys. And here, if you look at this period here, where we have waves less than 20 centimeters, we can see here that the two buoys are measuring the same conditions. So this is quite good data. And then we also done a similar test, but this time using the EMM2.0 buoy. So this was done in July 2016. And still in the Fjord. So as it is fjord conditions, it's usually small waves. And here the waves are mainly generated by light wind, or occasional ferry traffic. So if you look here on this graph, you can see that the wave height is less than 30 centimeters. And then we have, again, a very good correlation down to 6-7 centimeters.
So you say it's sufficient even for kayak paddlers, then, as you say here.
So if you need to go kayaking, then ask us for data.
Great. And so let's turn now to some other topic that has been sort of in the press for in the offshore environment, which is rogue waves, or freak waves that are occurring out of the blue and disappears, and that can cause a lot of damage. And I know that there's been a lot of research to try to pinpoint when does this occur and when is the likelihood of this occurring high. What did you find out about that when you worked with the researchers at the Meteorological Institute?
So the rogue wave is something that is a very unpredictable event. It is very difficult to forecast because they come out of nowhere and disappear without any trace. So they are rare and unpredictable and very difficult to forecast. So now from the theory, we can say that we can qualify a rogue wave by its steepness and the bandwidth. And this is described at what is called the Benjamin Fair Index, also BFI. So a high BFI will give a high probability for freak wave occurrence. So so far there have been some study and modelization done with that, but there is a lack of validation in open sea conditions. So this test that we have done at the Karmøy location has been a really perfect opportunity for this test validation. So here is what the Norwegian Met Office has been doing. They took some data results from the model for a year period from January 2017 to January 2018, and they look at they look at the BFI that is calculated. So you have here on the upper graph the mean BFI, and then on the lower graph the max BFI. So when the value is quite high, then we have high probability for freak wave. So then they expect that when you have a wave with a peak period in this area, with a significant wave height in this area, then you have a higher probability for freak wave. So then this region with this type of wave could be dangerous. So what we do now, if we look at the data that has been collected from the MOTUS buoy, we do the same exercise. We look at the peak period and the significant wave height, and we look at how the waves are spread out in this region. So this gives us this overview, and then we look at the probability for having a rogue wave in this area. So a rogue wave is specified more theoretically as the maximum wave height as 2.2 meters of the significant wave height. We also look at the steepness. So if you look at the blue circle, which are in this region here, then we have a probability for a rogue wave, where we measure a very high wave among the wave field. And if you look at the yellow one, we also here can see where there have been observed some very steep wave. And the red circle, they show the data that has been with these two conditions. So here you have very high probability for having a rogue wave. So when you have a smaller wave, I mean, it's not really dangerous, but when you come further up in this area, then you have it can be more dangerous for the mariners. So here we look here and there, and then if we just to generalize a bit, we can here see that this is where we observe the freak waves with the MOTUS sensors. And there is where the models say that the freak waves will occur. So here what we can conclude is that the results from the model are not in correlation with the observations, and the MOTUS buoys have been really good at catching up some rogue wave events. Now the Norwegian Met Office, they want to investigate a little bit more and see what could be the influence here with the currents and the wind information. So again, this is very valuable to have current and wind measurement in addition to the wave.
So basically here what we see is MOTUS is catching these rogue waves in a completely different conditions than what we are actually predicting with the models and the knowledge today.
Exactly.
Yeah, very interesting. So then we'll move on to some other experiments, and you know, we have been looking at some of these different types of setups to see what makes difference in terms of the usage of the buoys, in terms of accuracies and so on. And wanted to tell us a little bit about experiences with mooring, with and without using elastics or rubber cords.
So that's using rubber cords could be a problem in some applications. There have been some projects where we were not able to deliver rubber cords. So here we have done some testing as well with and without the rubber cord. But here again we work at a site that is 200 meter depth, so it's quite deep. But if you look on the left drawing here, that represent data with the rubber cord, we can see that we have very good correlation from the Thailand and the Waverider, both in the significant wave height and in the wave peak direction. And here is another data set without the rubber cord, where we only use ordinary rope and chain mooring, and then we can see here that we also have very good correlation. So we don't see any big difference, or at least no difference between using the rubber cord or not. Even if here you can see we have very the storm event with some waves up to 11 meter significant wave height.
Interesting. And then I think with with this 200-meter mooring that you were using a lot of you were using chain in combination with rope and in this mooring that you were experimenting with, right?
Mm-hmm.
Yes.
Yeah.
Okay. So we're already at the end, unfortunately, because we could hardly contain ourselves. We have a lot of things we wanted to share, but our host was very strict with us, so we had to select the best topics to share this time around. So in summary, we've gone through the first year deployments with the MOTUS buoy, looked at the data, looked at the wide range of users that we had and uses. And I guess we can say that common to them all is that, common to all the uses that we had is the need to really be able to measure accurate wave height and wave direction, along with other parameters from this flexible buoy solution. And that is interesting for us here to see who's taken this into use, who's using this today and how they're using it. So we're very thankful for all of our users who've shared their stories, and we have more stories than this that we've heard back from also. But we're very thankful because it just gives us also good feedback on where our buoys are utilized. Any final comments from you, Emily?
Well, you summarized quite well, but I mean, the MOTUS buoy, they have revealed their ability to measure waves accurately and also currents, and we can see that it is very valuable to measure several parameters because sometimes they can have a connection. They can help to explain what's going on in the ocean, as when we lose the signal from the Waverider. Here, when we measure the currents, then we can see that because this is due to the high currents. So it's quite interesting to have a multi-parameter measurement from the buoys.
Mm-hmm.
Yeah. Okay, so then we thank you for your participation.